You know, I want to start with something very ordinary, something you've probably done 1,000 times without thinking about it. Right now, wherever you're sitting, wherever you're watching this, I want you to reach out and tap something solid. A table, a desk, a wall. Go ahead. Feel that? Solid, right? Hard, real. You can feel it pushing back against your fingers. Your senses are telling you, this is here. This is real. This is matter. Now let me ask you something. What if I told you that tap, that solid, satisfying thunk, is almost entirely empty space? Not mostly empty, not kind of empty. I mean, if you were to scale up the nucleus of one of the atoms in that table to the size of a marble, a little glass marble about a centimeter across, the nearest electrons would be orbiting roughly a kilometer away, a kilometer, and in between nothing, just electric fields, and nothing. So what are you actually feeling when you press your hand on that table? You're feeling electromagnetic force. Your electrons repelling the table's electrons. Two clouds of charge refusing to overlap. You never actually touch the table, not in any deep sense. Your atoms and the table's atoms are pushing each other away, and your brain interprets that repulsion as solid. That's the game your senses are playing with you. And that is what this video is about. I've spent most of my life thinking about how nature actually works. Not how it looks to us, not how it feels to us, but what's actually going on underneath. And I have to tell you, the honest answer is this. Your senses are not giving you reality. They're giving you a summary of reality, a very useful summary, an extraordinarily well-engineered summary, courtesy of evolution. But a summary nonetheless, and in some places, a deeply misleading one. So let's talk about that. Let's really dig into it, because once you see it clearly, once you understand what your senses are actually doing, the world becomes, I think, about 10 times more interesting. Let me set something up first, because I want us to be precise here. I'm not going to wave my hands and say, reality is an illusion, like some mystical nonsense. That's not what I mean. The physics is very specific, and the mechanisms are real and understandable. What I mean is this. Your senses are detectors. They detect specific physical phenomena, certain wavelengths of light, certain frequencies of air compression, certain chemical concentrations, certain mechanical forces, and they convert those detections into signals that your brain then interprets. Now, and here's the key thing, the interpretation is not the same as the raw phenomenon. Let me give you the simplest example I can think of. Color, you look at a ripe tomato and you see red, beautiful, saturated red. But that redness, it doesn't live in the tomato. There's no red stored inside the tomato waiting to come out. What the tomato has is a molecular structure that absorbs most wavelengths of visible light, all the blues and greens, and reflects back photons in a very specific range of wavelengths, around 620 to 750 nanometers. Those photons hit the back of your eye, the retina, and they trigger a specific type of photoreceptor cell, what we call the L cone. That cone sends a signal to your brain, and your brain, through an absolutely staggering amount of processing, produces what you experience as red. Now here's the funny thing. The photon doesn't have a color. It has a frequency, an energy, an oscillation. The red is something your brain constructs from that signal. A different kind of eye, say, a dog's or a mantis shrimp's, processes those same photons and comes up with something entirely different. A mantis shrimp, by the way, and I find this delightful, has 16 different types of color photoreceptors. We have 3. What does a mantis shrimp see? I have no idea. I genuinely have no idea, and I love that I don't know. But the point is, the color you see is a construction, a model, an interpretation of physical data that evolution found useful. And this is true for every sense. Sound, you hear a voice, a melody, a thunderclap. But what exists in the world is a pressure wave, molecules bumping into each other, a pattern of compression and rarefaction traveling through air. Your ear converts that wave into nerve signals, and your brain builds the experience of sound. The music doesn't exist in the air. The pattern exists in the air. The music is in your head, smell, temperature, pain. All of them physical signals, converted, interpreted, and reconstructed into an experience that suits your survival, not necessarily one that suits your physics education. Now, I don't say this to be discouraging. I say it because it's the starting point. If you want to understand reality, Actual, physical, measurable reality. You can't just trust your gut. You have to build instruments, you have to design experiments, you have to do mathematics. And when you do that, you find out things that are genuinely, breathtakingly strange. Let's talk about light, because this is where I get genuinely excited. Light is one of my favorite things. You see a rainbow after a rainstorm, right? Beautiful arc of color, red on the outside, violet on the inside, all the colors between. Newton figured this out in the 1660s. White light, he showed, is not simple. It's a mixture. When you pass it through a prism, or, in the case of a rainbow, through millions of tiny water droplets, it splits by wavelength. Different wavelengths bend differently. You see the spectrum laid out. Now here's what that means. What you call white light, ordinary daylight, the light from the sun, is actually all those colors mixed together. Your eye can't separate them when they arrive together, so it averages them out and says, white. But white is not a wavelength. White is a sensation. It's what your visual system reports when it gets a broad mix of wavelengths and doesn't know what else to do with them. And here's what really gets me. The electromagnetic spectrum, the full range of electromagnetic radiation in the universe, goes from wavelengths shorter than an atomic nucleus all the way out to radio waves that are kilometers long. It's a vast, vast range. And visible light, the stuff your eyes can detect, is a tiny, almost absurdly tiny sliver of that range. A thin slice between roughly 380 and 750 nanometers. Think about that. There is vastly more electromagnetic radiation in the world than you can see. Radio waves are passing through your body right now. Infrared radiation is being emitted by your own skin, right now, as heat. X-rays are being blocked by your bones. Gamma rays from cosmic sources are sailing through you as we speak. You are bathed, constantly, in an ocean of electromagnetic phenomena you are completely blind to. You see maybe 1/10 trillionth of the electromagnetic spectrum. And yet, you walk around with a totally confident feeling that you're seeing the world. That you know what it looks like. Now I want to try a thought experiment. Imagine a creature, let's say a hypothetical creature, maybe a bat, though bats use sound, but imagine a creature whose visual system detected radio waves instead of visible light. What would a table look like to it? It wouldn't look like a table. A table is mostly transparent to radio waves. But the metal lamp on the table? That'd glow like the sun. The person sitting at the table? Practically invisible, but their heart, pumping blood, might create little pulsations of signal. Different detector. Completely different picture. Same room. That's not a fantasy. That's just physics. All right, here's another one that I think people don't appreciate enough. Let's talk about time, specifically, your perception of when things happen. Here's a question. When you see a friend clap their hands across the room, say, 15 or 20 feet away, do you see the clap and hear the clap at the same time? Your brain says yes. But physically, they can't be simultaneous. Sound travels at around 1,000 feet per second. Light travels at, well, the speed of light, about 186,000 miles per second, which, for any normal room, means light arrives essentially instantly, so the sound is delayed. At 20 feet away, the delay is tiny, maybe 20 milliseconds. But it's real. You can measure it. What's happening is that your brain is fusing these two signals, the visual and the auditory, and presenting them to your conscious mind as one unified event. It's doing some editing. It's saying, look, I know these arrived at different times, but they probably came from the same source, so let me sync them up for you. That's actually a remarkably useful thing to do. But it means your perception of simultaneity is not reliable. Your brain is adjusting the timestamps before you even get to experience them. Now take this further. Let's go big. When you look at the night sky and you see a star, let's say you see the bright star Sirius, you're not seeing Sirius as it is tonight. You're seeing it as it was about 8.5 years ago. That's how long the light took to travel here. You're looking at the past. All stargazing is time travel, in a very real, physical sense. And if you go further, to galaxies millions of light years away, the distant smudges you can see with a telescope, you're seeing those galaxies as they were millions of years ago. Some of them might not even exist anymore. We just haven't gotten the news yet. The light from the most distant things we can see took about 13 billion years to reach us. We are, in a genuine sense, looking almost all the way back to the beginning of the universe every time we point a telescope at the deep sky. Now your senses present you with a picture of what's out there, right now. But that picture is wrong. It's a mosaic of different moments, all arriving at your eye at the same time. Reality is not synchronized the way your perception suggests. I find this enormously exciting. Not disturbing, exciting. Because it means the universe is richer than it appears. It has more dimensions of structure than your unaided senses can report. Let me come back to that table you tapped at the beginning. Because I want to be more precise about what's happening there, because it's genuinely fascinating. An atom, as I described briefly before, is mostly empty space. The nucleus is tiny. Protons and neutrons packed together in a dense little bundle. And then, way out at distances that are enormous on an atomic scale, electrons. Now, why don't atoms just pass through each other? Why does the table feel solid? Two reasons, both quantum mechanical. The first is the electromagnetic repulsion between electron clouds. Electrons carry negative electric charge. Like charges repel. So when two atoms get close enough that their electron clouds start to overlap, there's a repulsive force. This is what you feel when you press on the table. You're pushing electron cloud against electron cloud, and they don't want to overlap. But there's a second reason, and this one is even more fundamental and, I think, more beautiful. It has to do with something called the Pauli exclusion principle. The Pauli exclusion principle, worked out by Wolfgang Pauli in 1925, says this: no two identical fermions can occupy the same quantum state at the same time. Fermions are particles with half-integer spin, electrons, protons, neutrons. And what this means, in practice, is that electrons in an atom can't all pile into the lowest energy state. They have to spread out, occupy different states. And when you try to squish two atoms together, the electrons resist. They can't all fit into the same states. There's a quantum mechanical pressure. It's not really a force in the ordinary sense. It's a consequence of the statistics of identical particles that resists compression. This is what makes solid things solid. Not some kind of underlying rigid substance. Not because matter is inherently impenetrable. It's because of electromagnetic repulsion and a rule about quantum statistics. When I learned this as a young man, really understood it, I remember thinking, all of civilization, every building, every bridge, every floor I've ever stood on, every hand I've ever shaken, all of that sturdiness and solidity comes from a quantum rule about identical particles. That's remarkable. That is remarkable. Now I want to talk about something a little more biological, but it connects directly to the physics. Because the gap between physical reality and what you perceive isn't just about the limitations of your detectors. It's also about what your nervous system chooses to report. And it is, in a very real sense, a choice. Or rather, a selection, an optimization. Here's an example. Your retina, the sheet of photoreceptors at the back of your eye, has a spot called the fovea, right in the center, packed with cone cells. That's where your high-resolution, color vision is concentrated. Move away from the fovea, and the resolution drops sharply. The peripheral visual field is low resolution, poor at color, better at motion. But you don't experience your vision as a high-resolution center surrounded by a blurry, colorless periphery, do you? The world looks pretty uniform to you. Pretty consistently detailed. Why? Because your visual system is constantly moving your eyes, little rapid movements called saccades, happening 3 to 4 times per second, and stitching together a composite picture. Your brain fills in the details, makes assumptions, and presents you with a seamless, high-resolution seeming image of the world. But it's a construction. A composite. An edited version. And here's the famous demonstration of this. Your eye has a blind spot, a place on the retina where the optic nerve connects, which has no photoreceptors at all. There's a hole in your visual field. Right now, as you're watching this, there's a chunk of your visual field where you simply receive no visual information. Can you see it? No. Because your brain fills it in. It looks at what's around the blind spot and makes a plausible guess about what should be there, and it renders that guess seamlessly. You never notice the hole. Now, that's an elegant trick. Practically, it works beautifully. Evolution found that filling in the gap was more useful than leaving a visible hole in the world. But epistemologically, from the point of view of understanding what's real, it's worth knowing. Your brain is making things up. Not randomly, not unreliably in any dangerous sense, but it's interpolating, extrapolating, filling gaps with guesses. I want to be careful here, because I know what temptation arises at this point in a conversation like this. People start to feel a pull towards saying, well, if our senses aren't reliable, maybe nothing is real. Maybe it's all illusion. That kind of thing. I think that's the wrong direction to go. And I'll tell you why. When I say your senses are giving you a summary of physical reality rather than the raw thing, I'm not saying physical reality doesn't exist. I'm saying it's richer than what you see. There's more there, not less. The atoms in that table are really there. The electromagnetic fields are really there. The quantum statistics governing the electrons are really there. These things are real, they're measurable, they're consistent, they make accurate predictions. The fact that your senses don't directly report them doesn't make them any less real. If anything, it makes the project of physics more important, because physics is the tool we've developed to go beyond what senses report and find out what's actually there. Now, I also want to say something about the senses themselves, because I don't want to be unfair to them. In the range of conditions they were designed for, and by designed, I mean shaped by evolution over millions of years, your senses are astonishingly good instruments. Your ear can detect pressure variations of about 10 picometers. 10 picometers. That's about a tenth of an atomic diameter. A vibration barely bigger than an atom is enough to be heard as a faint sound. The sensitivity is extraordinary. Your nose can detect certain chemicals at concentrations of parts per trillion. The experience of smell is chemically specific and incredibly sensitive in the right circumstances. And your eye, under ideal dark-adapted conditions, in the right conditions, can detect a single photon. A single photon. One quantum of light. That's as sensitive as a detector can be. So the instruments are not bad instruments. They're just not calibrated for physics class. They're calibrated for survival. And survival required detecting the things that mattered, predators, food, other people, at the scales and in the conditions in which humans lived. Not atoms. Not electromagnetic spectra. Not the speed of light. But here's what I find beautiful about the human situation. We were given senses calibrated for survival, and then, through this extraordinary process called science, through curiosity and mathematics and instruments and experiment, we figured out how to reach past what our senses report and see the deeper structure. That's a remarkable achievement. Maybe the most remarkable thing our species has done. I remember the first time I really absorbed what quantum mechanics was saying. I was young, a student, and it was genuinely disorienting. Not because I didn't believe it. I believed it. The math worked. The experiments confirmed it. But the picture of the world it implied, particles that don't have definite positions until you look at them, probabilities rather than certainties, interference patterns that suggest a particle takes multiple paths simultaneously, that picture didn't resemble anything my senses had ever prepared me for. And I realized, of course it doesn't. Why would it? My senses evolved to track rabbits and avoid falling out of trees. They weren't built to tell me about the double-slit experiment. That's not a failure of my senses. That's just their job description. All right, let's get into something specific, because I can't talk about the gap between perception and reality without talking about the most mysterious experiment in physics. I've described it elsewhere as the one experiment that contains all the mystery of quantum mechanics. I stand by that. Here's the setup. You have a source of particles. Let's start with electrons, single electrons, fired one at a time. You have a barrier with two narrow slits in it. And on the other side, a detector screen that records where each electron lands. Now, your common sense, your senses-derived intuition, says this should be simple. Each electron goes through one slit or the other. And on the screen, you should get two bright bands, one behind each slit. If you fired bullets at a wall with two slits, that's exactly what you'd get, two bands of bullet holes, one behind each opening. But that's not what happens with electrons. What you get, after many electrons have hit the screen, is an interference pattern. Alternating bright and dark bands, more like what you'd expect from waves than from particles. The electrons seem to be interfering with themselves, as if each one somehow went through both slits at the same time and the two paths interfered with each other. Now, and this is where it gets truly strange, if you put a detector at the slits to find out which slit the electron went through, the interference pattern disappears. You get two bands, just like the bullet case. The moment you observe which path, the electron behaves like a particle. The moment you don't observe, it behaves like a wave. What does that mean? I'll be honest with you, I don't know. Nobody fully knows. We know the mathematics of what happens, and the mathematics is breathtakingly precise and reliable. But what's physically happening, what really goes on when an electron travels from gun to screen, I cannot give you a picture that your senses would recognize, because there isn't one. Nature, at that scale, doesn't organize itself into the kinds of objects your senses are built to detect and track. This isn't a gap in our knowledge that will be filled in later. It's not that we need better instruments. The theory, quantum mechanics, makes predictions with staggering accuracy. It's just that those predictions are about probabilities and interference, not about the trajectory of a little ball going through space. The reality the theory describes is not a reality your senses can picture. It's more like a vast space of possibilities, and what we call observation, interaction with a measuring apparatus, is what collapses that space into a specific outcome. I find this equal parts frustrating and wonderful. I think you should find it that way too. Here's another thing your senses get completely wrong, and this one has consequences. Your senses tell you that space and time are absolute, that if I'm standing on a moving train and I throw a ball forward at 10 miles per hour, and the train is moving at 60 miles per hour, someone standing on the platform sees the ball moving at 70 miles per hour. Speeds add. That's what your intuition says. That's what Galileo said. That's what Newton assumed. It's wrong. Einstein showed, and this has been confirmed by countless experiments, that there's a maximum speed in nature. The speed of light. About 186,000 miles per second. Nothing with mass can reach it. Light and other massless things travel at it. But here's the bizarre part. The speed of light is the same for all observers, regardless of their own motion. If you're on a spaceship moving toward me at half the speed of light, and I shine a flashlight at you, you don't measure the light arriving at 1.5 times the speed of light. You measure it arriving at exactly the speed of light. Same as if you were standing still. How can that be? If speeds are supposed to add, how does light always go the same speed? The answer, and this is Einstein's radical insight, is that space and time themselves are not absolute. Time runs differently for observers in relative motion. Distances contract along the direction of motion. These are not optical illusions or measurement errors. They are real, physical effects. Clocks on fast-moving objects actually tick slower. This has been measured with atomic clocks on airplanes. The effect is small at airplane speeds, but it's there. Your senses perceive space and time as a fixed, universal backdrop. They perceive simultaneity as absolute. If two things happen at the same time, everyone agrees they happened at the same time. But that's not how the universe works. Simultaneity is relative. Two events that are simultaneous for one observer are not simultaneous for an observer in motion relative to the first. This isn't a quirk or a special case. It's fundamental. And yet, you've never once noticed this in your daily life. Because you've never moved at a significant fraction of the speed of light. At human speeds, the effects of relativity are completely imperceptible. Your senses evolve in a world where the effects of relativity were too small to matter, so they don't report them. Once again, the senses aren't wrong for practical purposes. They're just not giving you the complete picture. I want to tell you something personal, because I think it matters for how you approach all of this. When I was a young man studying physics, really getting into it, at MIT and then at Princeton, there was a process that happened to me that I didn't fully anticipate. A kind of progressive unlearning of the obvious. One by one, the things that seemed self-evident, the things that felt like just how the world is, turned out to be approximations, or illusions, or special cases of something much stranger. Color, an experience in your brain, not a property of objects. Solidity, electromagnetic and quantum forces, not substance. Simultaneity, relative, not absolute. Position, in quantum mechanics, not even well-defined until measurement. Causality, subtle and more complex than it appears. Was that disorienting? A little. But mostly it was exhilarating. Because each time a seemingly obvious thing turned out to be more complicated than it looked, there was something real and specific and understandable underneath it. Not a void, not chaos, just a deeper layer of order. A more precise and surprising truth than the naive version. I think this is what people miss when they're taught science as a list of facts. Facts can feel like a burden, things to memorize, things to get right on a test. But the process of going underneath the obvious and finding something stranger and more precise, that's the fun part. That's the adventure. And the thing about your senses, about recognizing what they are and aren't telling you, is that it's an invitation. It's an invitation to go further. To ask, if this is what my senses report, what does the evidence actually show? What do the instruments say? What does the math predict? What happens when I test it? That's the scientific attitude. Not cynicism about perception. Not despair about reality. An invitation to go look. Here's a lighter thought experiment, just to change the pace a bit. Imagine you lost your sight. Now, I don't wish that on anyone, and this is purely a thought experiment, but imagine it. How would your model of the world change? You'd rely much more heavily on sound. The shape of a room, you'd learn to map it from echoes, the way sound bounces off walls, the way it differs when there's furniture present or absent. Blind people who become skilled at this can navigate complex environments, detect doorways, identify objects, all from sound. The information is there in the acoustic field. We just usually don't bother to extract it because we have eyes. Or smell. A dog's world is largely a world of scent. A dog's nose has something like 300 million olfactory receptors compared to a human's 6 million. The olfactory cortex, the brain region devoted to processing smell, is proportionally much larger in dogs. A dog can follow a scent trail that's hours old. It can detect a cancer in a body through smell, something we're now seriously trying to use medically. It can identify individuals, read emotional states, detect fear. The world a dog navigates is deeply, richly detailed, but in a dimension that's almost invisible to us. We walk through the same garden and think, pretty flowers, nice day. The dog is reading a three-dimensional map of who was here, when, what they were feeling, what they ate. Same physical reality. Completely different information extracted. Completely different experienced world. Now here's the physics lesson in that. The chemical signals the dog detects are real. The volatile molecules in a scent trail are there. We're not detecting them, but they exist. The dog's experience is, in that sense, more accurate to the full richness of what's physically present than ours is. This is what I mean when I say your senses give you a summary. A useful, serviceable, human-calibrated summary. But not the whole thing. Temperature seems absolutely real to your senses. You feel cold. You feel warm. You feel hot. These sensations are immediate, vivid, reliable, right? Well, go into a room that's 50 degrees Fahrenheit and pick up a metal spoon and a wooden spoon that have been sitting there the same amount of time. Touch them both. The metal one feels colder. Much colder. But they're the same temperature. The thermometer says so unambiguously. Both are 50 degrees. So why does the metal one feel colder? Because what your skin is detecting is not temperature. It's heat transfer rate. Metal conducts heat much more rapidly than wood. So when you touch the metal, heat flows out of your hand quickly, and that rapid heat loss is what your skin reports as cold. The wood conducts poorly, so heat leaves your hand slowly, and your skin reports not as cold. Your skin doesn't have a thermometer. It has a heat flow sensor. And it's giving you information about thermal conductivity, not about the actual temperature of the object. Your brain then interprets that as temperature, because in most everyday situations that's a useful shorthand. But it's not measuring what you think it's measuring. This is one of my favorite examples because it's so simple. You can test it right now if you have a metal spoon and a wooden spoon and a cool room. And yet the discovery that what you feel as cold is not the temperature of the object is genuinely counterintuitive. Your senses have been quietly, helpfully, completely lying to you about this your whole life. All right, let's bring it together, because I've taken you through a lot of territory and I want to be clear about what the lesson is. The senses give you a model of the world, a representation, a construction built from physical signals, processed by an evolved nervous system, optimized for the survival and functioning of a primate animal in a world of medium-sized objects at moderate temperatures moving at slow speeds. That model is useful. I'm not asking you to distrust it for everyday purposes. Cross the street, trust your eyes about the car coming. Pick up the hot pan, trust your sense of heat. Recognize a friend's face, trust your vision. But when you want to understand nature, when you want to know what's actually there, how things actually work, you have to go further. You have to use instruments that extend your senses into ranges evolution never prepared you for. Telescopes and microscopes and particle accelerators and radio receivers and spectrometers and interferometers. You have to use mathematics to describe patterns your eyes can't see. You have to use experiments to test hypotheses that feel wrong to your intuition. And here's what you find when you do that. Reality is not simpler than it appears. It is vastly richer. The atoms, the fields, the quantum behavior, the curvature of spacetime, all of it is there, real and precise and describable, just not visible. What you also find, and I think this is underappreciated, is that the universe doesn't care about your intuitions. Nature has no obligation to make sense to a nervous system that evolved for a completely different purpose. And the history of physics is, in large part, a history of our intuitions being wrong. Newton's mechanics felt complete and obvious and final. Wrong, or rather, a special case. The Michelson-Morley experiment showed the ether doesn't exist and the speed of light is constant. Counterintuitive. True. Quantum mechanics showed that particles don't have definite positions before measurement. Deeply counterintuitive. Extraordinarily well confirmed. Every time nature surprised us, every time the universe turned out to be different from what common sense predicted, we learned something. We pushed our understanding further. And that further understanding has consequences. Transistors, lasers, MRI machines, nuclear reactors. The entire edifice of modern technology rests on physics that contradicts everyday intuition. So the question isn't, should I trust my senses? The question is, for what should I trust them? For getting around the world, yes. For understanding the structure of matter, the fabric of spacetime, the quantum behavior of particles, no. For those, you need something more. You need the tools that humanity has painstakingly built to go past what senses report, the tools of physics, of mathematics, of rigorous experiment. And I find that deeply satisfying. Because it means the world is not exhausted by what I can see and touch and taste and hear. The world has more in it than my senses tell me. Isn't that exciting? There's more. There's always more. The most important thing about recognizing the limits of your senses is not to feel smaller. It's not to feel cheated or deceived. It's to feel curious. To let the gap between what you sense and what's there be an invitation to look harder, think more carefully, invent better instruments, devise more elegant experiments. When I look at a flower, and I've been asked about this, I can see the beauty that everyone sees. The colors, the shape, the symmetry. But I also see the physics. The way the pigments absorb and reflect specific wavelengths. The way the structure is optimized by evolution for the eyes of bees, which see ultraviolet patterns on petals that are invisible to us, landing guides for pollinators, painted in frequencies we can't detect. And that doesn't diminish the flower for me. It makes the flower astonishing. There is a secret world painted on every petal, a world your eyes can't see, a world that's been there all along, that the bees have always known about, that we only discovered when we built instruments to look. That's the universe. Everywhere you look, if you look carefully enough, there is more than meets the eye. More, not less. Deeper, not shallower. And that, to me, is the most beautiful thing about physics. It doesn't take wonder away from the world. It shows you how much more there is to wonder at. The table is real. The atoms are real. The electromagnetic forces are real. The empty space is real. The quantum statistics are real. Your senses gave you the table. Physics gave you the rest. And the rest is extraordinary. Thank you.